So for simplicity, let's assume that F contains K. I can always achieve this just by base changing my curve up to F. Or up to like the composite of F and K, which contains K. Okay? So for each prime, so P with a long tail is going to mean a prime of F. P with a short tail is going to mean a prime of K. So for each prime P with a long tail of F, where E has good reduction. I know. I don't want to be confusing. All right. So for each prime like this, where E has good reduction, right? Consider the reduced curve E bar. I'm going to call this E bar sub P, and this is a curve over O F mod P. Right? It's going to have a Frobenius endomorphism, which I'm going to call phi sub P with a long tail, and it's given by, just on coordinates, it's x, y to x to the norm of P, y to the norm of P. Okay. Right. So I'm going to state the next result, assuming that the ring of endomorphisms is the full ring of integers, and by a theorem of Shimura, that will suffice because any elliptic curve is isogenous to an elliptic curve with any elliptic curve with complex multiplication by an order is isogenous to one with complex multiplication by the full ring of integers in the same field, and isogeny doesn't change in L function. So here's kind of the key point. So I'm putting dot dot dots on both sides of Deuring and Shimura. These results were sort of known before Deuring, but stated in this language by him. Shimura has restated and generalized it, and probably my language is more of a modern language, but the essential facts of this theorem are really Deuring and before. Okay, so first of all, the reduction map end E to end E P with a long tail is injective. This actually isn't too hard to prove. What's this map quickly? Like an endomorphism in algebraic geometry is given by some polynomials, and so it makes sense to reduce the polynomials mod P, and that gives me an endomorphism with the reduction of the curve. That's this map, and the fact that it's injective is the statement of this first part of the theorem. The image of the reduction contains the Frobenius of E with a bar on top and a P on the bottom. Okay, so this is the key to the whole theorem. This curve is defined over a number field, but it has some endomorphism which reduces mod P to the reduction to the Frobenius of a curve defined over a finite field. So if you understand nothing else from the talk, it's that we can lift Frobenius from characteristic P to characteristic 0. That's why Deuring's theorem works. Okay? 3, the third part of this theorem is that there is a map psi from the idels of F down to K, and it's, sorry, I should say there's a unique map psi satisfying the following 3 conditions. So the first condition is that I want psi to be continuous, but like what topology should a number field get? So I want to be an atheist on what topology K has, and the only way to do that and still be fair to everyone is to give it the discrete topology. And so we're just going to say the kernel is open. Okay? B, the restriction of psi, so f cross sits diagonally inside the Adels, and I demand that the restriction of psi be the same thing as the norm map. From f cross down to k cross. And the third thing I demand is that, so let's say I take the Adel that is 1, 1, dot, 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 1, then I pick a pi in the p spot. Then I demand that this be, so this is going to land in k cross a priori, right? Which means it could land on the endomorphisms of the curve. And I demand that it lands not on any endomorphism of the curve, but on the lift of Frobenius guaranteed by B. By part B of the proposition, and it's unique by part A of the proposition. Okay, so notice that this is not a Hecke character, because to be a Hecke character, Tate showed you have to be defined on the Adel class group, which means that on F cross, you have to be trivial. But condition B over there says that, I switched from numbers to letters, sorry about that. Right, condition B says that this guy's going to be a norm. But there's an easy way to fix that. So, I just use this board. Okay, so how do we fix that? We just define a character by taking this character and then going to K tensor R. This is isomorphic to C cross with a choice of basis, which is equivalent to choosing a complex conjugate of I. This is just the map that takes x. It takes psi of x, but then it dumps out the norm of psi infinity. So this will be trivial on the image of F cross, and so it'll give a Hecke character. Okay. There's also a map psi c bar, which is the same map, sort of with the opposite isomorphism here. Or equivalently, just do this map and then bar. Okay. And Deuring's theorem on the, exactly says that the L function of E over F product of the L functions of these two Hecke characters, psi and sigma. I've been a little bit glib about something, which is I've said this is defined like this, but remember this only makes sense if P with a long tail is a good reduction prime. So it's generally the conductor of the curve, but the conductor of the character, which I'll call fractor F. I'm going to call it conductor of psi F. That's what all conductors are called. And the point is that it's divisible by precisely the primes of bad reduction.